Hi guys, let's try to do some comparative study between electrostatics and magnetism. So in electrostatics, we are having charges. These charges are positive and negative. But in magnetism, no monopoles. Or here you write as monocharge. That is also correct. In electricity, monocharges exist. But in magnetism, no monopoles. This electricity we used to represent with the capital E, but in magnetism, we represent that with capital B. And in electricity or electrostatics, so we have electric dipole. So this is electric dipole. One is positive charge, another one is negative charge, having a dipole length of 2L. So if it is dipole, it's having dipole moment, that is represented with P equal to 2Lq, which is the dipole moment. And dipole moment having direction. So the dipole moment direction, if you take, the dipole moment direction is from negative charge to positive charge. So this we know as electric dipole. So this term we known as electric dipole. So when it comes to magnetism, so this is the basic element. So in magnetism, we are having a bar magnet, or which also known as magnetic dipole. So this known as magnetic dipole, which is having two poles, north to south, north and south. If we represent dipole moment P in electrostatics, in magnetism we used to represent that with little m. So magnetic dipole moment. So we got an expression for magnetic dipole moment that equal to m cross b. So this magnetic dipole moment, if you want to write like this, so we can write that as here 2L equal to the length of the bar magnet 2L times Q suffix M. So here Q suffix M is magnetic pole strength. Magnetic pole strength. And when it comes to direction, so this is direction for electrostatics, electric dipole direction, dipole moment direction, minus charge to plus charge. So this is electric dipole moment. When it comes to magnetic dipole moment, the direction is from south pole to north pole. That is the magnetic moment direction. And moreover that, if we can do one comparative study at here, in electricity we used to use a constant as 1 over 4 pi epsilon naught. But when it comes to magnetism, so that constant value will become mu naught upon 4 pi. So this you can understand if you see the derivations, compared to derivations in the both the cases. And when it comes to electric field lines, so the electric field lines for an electric dipole, this is for electric dipole, and this is for magnetic dipole. So magnetic dipole is equivalent to bar magnet, or which is also equivalent to a current carrying solenoid. Okay, so this electric field lines properties we studied the for charges, and the same electric field lines properties here when it comes to magnetism it turns as magnetic field lines. And here we always used to use a word known as electric flux. How you define electric flux? The number of electric field lines passing through a unit area we define as electric flux. Similarly, when it comes to magnetism, so we define that as magnetic flux. Flux means number of field lines. Magnetic flux. And if you can see the direction, the electric field line starts from positive charge and ends at negative charge. But when it comes to magnetism, so we don't say any specific starting and ending of the field lines. So there is no origin of the field lines. From there it starts. There is something is peculiar. But when it comes to direction, when you can see inside the magnet, inside the bar magnet, the field lines are passing from south pole to north pole. The magnetic field lines inside the bar magnet passing from south pole to north pole. And number of field lines gives that flux density. Same sentence. And both of the cases. Magnetic flux density and electric flux density. If number of field lines are more at that point, electric field strength is more in electrostatics. Similarly, when it comes to magnetism, when number of magnetic field lines are more, there the magnetic strength is more. So that's the reason magnetic strength is more at poles. The very needed difference at here, needed difference in electrostatics, the electric field lines do not form closed loops. Do not form closed loops. But when it comes to magnetic dipole, so they do form. They do form closed loops. So this field lines gives them geometrical interpretation of the electric field lines between the electric dipole, likely here for the bar magnet too also. So if I write further as compared to analog study between the same concept we are having dipole concept in both electrostatics and in the magnetism. Let us try to see how this terminology difference will be there. So as a constant we are using 1 over 4 pi epsilon naught in electrostatic. So in magnetism this constant will be turns to mu naught. So when it comes to dipole moment, in electrostatic we are representing with that P, and when it comes to magnetism it represents with the little m, lowercase m. Now when it comes to equatorial electric field for short dipole, for dipole electric field along equatorial. Along equatorial, we can write that as minus P upon 4 pi epsilon naught r cube. So in the magnetism also we are having the same concept, but here that is a magnetic dipole. Only the term gets changes. Magnetic dipole. So that becomes as minus mu naught times m upon 4 pi r cube. They both are similar in characters. Now when you take along axial point, so this is 2p times 2p upon 4 pi epsilon naught r cube. But when it comes to same concept in the magnetism, so this turns as mu naught times 2m upon 4 pi r cube. Both have the same formula, but the terms dipole moment only changes and constant 1 over epsilon naught and mu naught. Apart of this, dipole in external field. When electric dipole in an external electric field, so it experiences torque. So in both cases it experiences torque. So the torque here represents P bar cross E bar or P sin theta. So in magnetism it represents M bar cross B bar. Not only that, if an electric dipole, if dipole in an electric field, it's also having energy, potential energy. So the concept of energy comes for a dipole in an external electric field or magnetic field. So here the formula goes to minus P dot E, dot product of dipole moment times electric field, but here goes to minus M dot B. So if you observe this analogy carefully, everything is matters of dipole moment P and magnetic moment M. And only the difference constants 1 over epsilon naught in electric field and mu naught in magnetic field. So when you can compare the electrostatics dipole in all the cases from the beginning to till the whole concept of dipole, equatorial and axial, is electric field strength and magnetic field strength, and above that torque experienced by an dipole in an electric field, similarly in magnetic field also, and dipole energy also. So if you see, a lot of similarities you can see, especially in the concept of dipole. And the dipole is the very basic in magnetism, means very starting, because in magnetism there are no existence of monopoles, because no monopoles in magnetism. Now apart of that, we need to discuss one more thing, that if you remember, to calculate the electric flux, we are depend on the Gauss theorem. So in electrostatics, the Gauss law help us to find out the electric field. So the same Gauss law, so in magnetostatics also, or in magnetism is also exist. So that I will discuss as a separate concept, but the analogy study between the electric dipole and the bar magnet or magnetic dipole. So try to interlink all these concepts. If it is a dipole, the needed concepts to cover on the both of the cases: field at axial point and equatorial point. So this is the derivation, and a part of that, flux, and in the both of the cases, electrostatic magnetism, field lines diagram, and a part of that, torque, and finally energy, potential energy most. So these are the common concepts and important concepts, and these concepts almost all occupies the chapter more than 50%. So whenever you can study this concept, if you can very good at in either electric fields or magnetism, you just easy to apply it to another concepts. Means if you are very familiar to this concept, all concepts in the electrostatics, they are very easy, very handy when it comes to magnetism or magnetostatics. The one and only major difference comes at dipole moment. It is P, it is a 2Lq in electrostatics, but in magnetism it will becomes 2Lq suffix M. That is magnetostatics. So dipole moment is very important concept to understand all these concepts. So let us go further. So how this Gauss law helped us in electrostatics to find the electric field of any given surface. Similarly, we need to discuss the Gauss law in magnetostatics too also. That I will discuss in another video lecture.